Hey, welcome back. So here we are with our chemistry lesson for today. It's our second lesson. We're looking at a very important topic, and that is significant digits. This is a topic that's going to be with you from now until the remainder of the school year, really, in this class. So very important notes today. So without further ado, let's take a look where we're at and get going on significant digits. So here's where we left off. Working with derived units. Turning the page here. Today, we're looking at significant digits. So significant digits are the meaningful digits, the important digits, and a measured or calculated quantity. And that's going to be important that we're looking at measured or calculated. We'll talk about defined quantities and exact quantities and counted quantities in a few minutes here. So important though that the significant digits are only when you're measuring or calculating numbers. All right, first step, we have to know how to identify significant digits. And often, and mostly from here on out, significant digits I just kind of abbreviate as SD. So not writing significant digits every time. So first of all, we have to be able to count these guys, know what is and what is not a significant digit. So our first rule here is that any digit So our first rule here is that any digit that is a non-zero number is significant. So a couple of examples, if we have a count for say, a measurement for say like 845 centimeters, well, the 8, the 4, and the 5, they're all not zero. So this value would have 3 significant digits, the 8, the 4, and the 5. Doesn't matter if there's a decimal point or not. So 1.234 kilograms. Doesn't matter if there's a decimal. All of these digits, 1, the 2, the 3, and the 4, are all non-zero. So this one has 4 significant digits. So all non-zero digits are significant. Onto the zero rules. When is and is not a zero significant? So zeros between non-zero digits. We call these sandwiched zeros. Sandwiched zeros, when they come between non-zero digits, they are considered significant. So 606 meters. Well, the 6 and the 6, they're both non-zero digits, so they're significant. And then the 0 there is in the middle, it's sandwiched. So it too is a significant digit. So 606 meters would have 3 significant digits. So there's more numbers sandwiched. For instance, 40,051. There's the unit joules there. That little J stands for joules. It's a measure of energy. We'll get to that more second semester. But this number here, okay, has a 4, a 5, and a 1. So those 3 are all significant. And then the 0 and the 0, they're sandwiched. So they are significant. They're placeholders. So this one has 5 significant digits. Right place here. So zeros to the left of the first non-zero digit are not significant. So when you're looking at your number, always find your number first. Anything to the left of that first number is not considered significant. So 0.08 liters has just one significant digit, just the 8. These zeros here are what we call leading zeros. They're on the left of the first number. They lead the number, not significant. And it doesn't really matter how many there are. It's a very small mass right here. We have 0.0000349. Well, our first actual number there is 3. The zeros to the left of that, the leading zeros, they don't count. So we only have 3 significant digits here. So none of these zeros count, only the 3, the 4, and the 9. All right, so we just discussed zeros to the left of the very first number. How about zeros to the right of the very last number? Well, these are significant if there is a decimal point in the number. 2.0 micrograms, 2 significant digits. The 2, that's a non-zero number, and then the 0, it's on the right of the number, and there is a decimal point there. So 2.0, 1 digit, 2 digit, there's 2 significant digits in that answer there. .040, well, the 3 and the 4, they're both non-zero numbers. There's a sandwiched 0, so we know that counts. There's a trailing 0, a 0 to the right of the last number. It counts because there is a decimal point. So this one has 1, 2, 3, 4 significant digits. How about zeros to the right? I mean, we call these trailing zeros, the ones that are to the right of the last number. They're not significant if there is not a decimal point. So $1,000, 1,000 anything, has just one significant digit. Just the one. There is no decimal point. Versus the same exact number, but with a decimal point. So $1,000 with a decimal point. This one would have 4 significant digits. That decimal point means that those trailing zeros are significant. So the 1 is significant. Each of the 3 zeros is significant. This one has 4 significant digits. And again, the big difference is it has a decimal point, whereas the first 1,000 Did not. Exact numbers obtained from a count or from a definition have infinite significant digits. So this past summer, the United States won 39 gold medals in the Summer Olympics. That is a count. There is no doubt in anyone's mind that that is exactly how many we won. It's a count. So this has infinite significant digits. That count, that number of gold medals is not a measure, it's a count, has infinite significant digits. How about a definition? What do we mean by a definition? Well, we actually worked with these on our last section of notes. One meter is equal to 1,000 millimeters. Well, that's an exact definition. There is exactly 1 meter in exactly 1,000 millimeters. So this definition also has infinite digits. So we don't use counts or exact definitions. And that kind of goes back to our definition of what significant digits are. Quick conceptual check for you. So every once in a while, you're poised with a problem where you got to kind of think outside the box. For instance, how can you write 1,000 milliliters with exactly 2 significant digits? Perhaps you're noticing the problem that we have here. Perhaps you've given it a shot. Perhaps you're thinking about it. If I were to write just 1,000 milliliters, well, that's just 1 significant digit. So this doesn't work. If I were to add a decimal point at the end there, well, now that decimal point makes all of these trailing zeros significant. So this would be 4 significant digits. Also, not exactly 2. Doesn't work. So the trick to this problem here is we actually have to combine what we learned on the first day and use scientific notation. 1.0, there we have a trailing zero. That is significant, but only one of them. And the 1 obviously is a non-zero digit, so it is significant. Times 10 to the third, that gives us 1,000. There's our milliliters, and that has our 2 significant digits. So kind of thinking outside the box. And every once in a while, you have a problem that you do have to write in scientific notation in order to get the proper number of significant digits. All right, next up, we're going to take a look at operations with significant digits. By operations, we mean mathematical operations like addition, subtraction, division, and multiplication. Depending on which operation you're doing, we've got a different set of rules. So we'll start up with addition and subtraction rules. So if you are doing addition and subtraction, the rule is rule is quite a mouthful, and reading it may not help a whole lot. The number of digits after the decimal point when you're adding and subtracting is determined by the lowest number of digits to the right of the decimal point of the original number. Again, that's saying quite a bit. Easier, I think, to demonstrate with an example. So here, we'll take a look at an addition example. (89.332 centimeters plus 1.1 centimeter. First thing, just go ahead and do your addition, do your operation. You can use a calculator. There's no rule saying you have to go by hand, but for this one, I'm just going to go ahead and do that. Here's my unit. So 90.432. Well, we need to know where to round. I've had people ask me all the time, do we just always round to the 10th place for this class? No, the answer is absolutely not. You have to know how to round based on how many significant digits this answer should have. It's an addition problem. So again, what that means, addition and subtraction, is that we're limited to the placeholder, or how many places after the decimal, of our answer with the fewest places after going past the decimal. So this first number here, 1.1, has only one significant digit after decimal. So guess what? Our answer should only go to that 10th place, only that first place after the decimal. So the next thing I like to do then is underline my extra digits. So there I have my 3 and my 2 underlined. And then finally, I'm going to, my final answer, I'm going to round, oops, not red, round just one place after the decimal. Our rounding rules, we look at the 4, we look at the next number after the 4, it's a 3. If the number is 5 or greater, we go ahead and round 4 up. If it's less than 5, as is the case here, we're just going to keep it at what we have. So 90.4 centimeters is our final answer. And let's then get in the habit of putting it inside of a box so we know what the final answer is. So 90.4 centimeters is the answer to that question, correctly rounded and with correct number of significant figures. Do one more example here. A subtraction step. The rule is the same for subtraction or addition. So 2.097 grams minus 0.12 grams. Again, let's start off by just go ahead and doing the math. And again, if you want a calculator for that, that's absolutely fine. There's no rule that says you can't have that. So I do my math, I get 1.977 grams. Next step, 2 significant digits in this value here, the 0.12, 2 significant digits after the decimal. So I underline my extra digit. I want the 9 and the 7. There's my first 2 digits after the decimal. I'm going to underline that last 7. It is not significant. And then finally, follow my rounding rules to get just 2 numbers after the decimal. 7 is enough to round up, so I'm going to call this 1.98 grams. Put it in the box, and there we go. Final answer. Next up, we're going to take a look at our multiplication and division rules, and these are a little bit different. So the number of significant digits and the final answer is determined by the original number that has the fewest number of digits. Again, tough to say, tough to write, tough to read. I think an example will help a lot. So 2.8 meters times 4.5039 meters. Again, first thing we're going to do is just start off by doing the actual math. Pi on there. What we want is 2.8 times 4.5039. Press the compute button. $12.61092. That's the answer my calculator spitting out. Hey, watch your units on this. Meters times meters is not meters. It's meters squared. It's like 5 times 5 is 5 squared. 2 times 2 is 2 squared. The same thing, meters times meters is meters squared. So next, I want to count the total number of significant digits in each of these values. This one has a 2 and an 8. That's 2 significant digits. This one has the 4, the 5, the 0 is sandwiched, so it counts the 3 and the 9. That's 5 significant digits. We're going to be limited to 2 total significant digits in our answer because this value is a smaller value than the 5 significant digits here. So our final answer should only have 2 significant digits. There they are, the 1 and the 2. That's it. Everything else, again, I'm going to underline. It is not significant. And now we'll go ahead and round. The number after 2 is a 6. That is enough to round up. So I will do that, and I will end up with 13 meters squared. Again, the rules are a little bit different for multiplication and division than they are for addition and subtraction. So now we have our mass over volume. Looks like we're doing a density calculation. So it's divided by. So we're going to follow the same rules we did before. I'm going to start again by just plugging into my calculator 6.85 divided by 112.04. Press the compute button. Oh boy, that's a lot of numbers there. So let's use a little trick. So I'm looking at this number and I'm already thinking, hey, I'm learning these rules. I know that this is only 3 significant digits. This one has more than 3. I'm going to be limited to just 3 significant digits. These zeros don't count. They're leading zeros, and leading zeros never count. So here are my 3 significant digits. The general rule is you need to carry at least 2 extra digits. So I don't need to write all of these. It'd be a lot of writing. It's a lot of extra digits to be carrying around. So I'm just going to write 38. There's my 2 extra digits. I'm going to make sure to underline it, and then always have units on this on these calculations. So grams per milliliter. Now I can go ahead and round to my correct number of digits. 3 is not enough to round up, so I'm going to keep that at 0.0611 grams per milliliter. Put my box around it, and there we go. There's our appropriate number, rounded the appropriate number of significant digits. Hey, watch out for exact numbers. Watch out for those numbers we talked about, like the 39 gold medals. Maybe you wanted to figure out how many medals, gold medals, were won per athlete. Well, you're not going to be limited to the 39 gold medals because there's infinite digits there. That is an exact number. Similarly, our definitions, 32 centimeters. A lot of people see this here and they say, oh, there's just 1 significant digit. The 100 only has 1 significant digit. The 1 only has 1 significant digit. Not true. These are definitions. These are exact. So this conversion is a definition that has infinite significant digits. I'm not going to be limited by the number I have. So my 32 centimeters I'm going to end with 2 significant digits. That's where I started with. Again, these here have infinite, so they're not going to limit the number I'm working with. So watch out for that. I have a lot of people try to say there's only 1 digit there, and it's not accurate. There are infinite digits there. All right, finishing up. The reason we have significant digits. The reason for significant digits. So I cook, I bake, and some of those things in cooking instructions and ingredients, they bother me. Like a pinch of salt. Well, I've got pretty thick fingers. My pinch of salt might be larger than yours. A drizzle of oil, that to me seems completely made up and completely arbitrary and can get me in trouble sometimes. I cooked some delicious hamburgers last night and I put a drizzle of oil down on the pan before I cooked them. Tonight, maybe I try to duplicate that success and I have a much larger drizzle because I don't know exactly what a drizzle is. My hamburgers come out too greasy and I've ruined my meal. Chemistry, we don't like to do that. Chemistry, we have significant digits and they help us not do that. Significant digits show us the precision of our instruments. So how precise are the tools that we are working with? That's what significant figures do for us. Here's a rule. Make sure you guys get this rule down. Every time you take a measurement, always guess. Always guess one more place than what you know, unless the tool is electronic. It's electronic, you only report what you have. And we do use electronic balances pretty often, but otherwise always guess one more place than what you know. So as an example, measure this line, not a very straight line, but we'll measure this line. And we'll use my little fabricated ruler here. To do that. So looking at the ruler, we know beyond a doubt that this line is at least 2 centimeters, between 2 and 3. So that is not an unknown number. That is a reasonably determined number. We know that for a fact. That shows our value there. So I'm going to say 2 centimeters. And then here's the thing. We always guess one more place. Now, it should be a reasonable guess, should be an educated guess. So roughly in here is about halfway between 2 and 3. So I'd call that 2.5, and we're less than that. So I'll go ahead and make my guess. I'm going to say 2.2. If you thought it looked like 2.3, that's awesome. That's perfectly all right. If you said it was 2.1, I'd probably be right with it. 2.4, okay. I'm not going to argue with you. But this digit right here, and it's supposed to be red. It's not showing up all that well there. Well, take my word for it. That is a red number. Shows up very clearly to me. Unfortunately, I'm looking at the screen here, and it's not very red on the screen. Well, that is our degree of precision. That shows anyone who comes in the future, it shows them exactly how good of a tool you used and exactly how precise they need to be. That is our final significant digit. And that's why significant digits are important. Shows you, hey, with this particular tool, we were able to measure 2.1 centimeters. That's how precise we measured this line. You saw a recording that said 2.5, 4, 5, 6, 7 centimeters. You'd know, wow, they used a really precise instrument to get that recording. You have to go a lot of little points in between these centimeters to get that good of a recording. So for those of you who bake, you read 1 cup of flour. Well, guess what? You can go a little bit over. You don't have to be perfectly at 1 cup. You don't have to sit there and eyeball it and take some off and put a little back in. You don't have to do that. It just says 1 cup of flour. It could be a little over, it could be a little under. It's okay. But now that you understand significant digits and you're making cookies, if it says 1.0000 cup of flour, you know you better spend some time making sure you have exactly 1 cup of flour, because this is a very precise measurement. If you want to get the cookies tasting exactly like the recipe says, you know you got to use a very precise measurement. And that's the importance of significant digits. Only 1 significant digit, 5 significant digits. It shows us how precise of a measurement we need to make. Well, that ends today. Pretty long lesson today, so I apologize for that. But we got through it. And again, you're gonna fall back to these notes a lot this year, so I hope that they help. I will see you guys next time.